Hi, everybody. My name is Dmitry Livshits, and I would be host of the webinar today. So today we will discuss why storage for AI matters the most. AI workloads are pushing storage demands not only for traditional HPC, but as well for enterprise AI infrastructure. And AI class storage is no longer just a special requirement, it's as well enterprise team need for now. At the same time, what we see is that NVMe remain constrained, what keeps many conventional high-performance storage systems expensive and hard to source. So in this webinar, Xinnor, Supermicro, and AMD will walk through xiNAS, a shared storage platform built to bring the best possible level of performance for wider set of teams. Solutions runs on Supermicro service with AMD EPYC processors and has been validated for AI and HPC workloads. The goal is very simple: high throughput, strong resilience, and simpler operations that most HPC-style storage stacks. So today with me, I would like to introduce my colleagues who will help me in this webinar. From AMD side, we have Sachin Hindupur. Sachin is a global lead for strategy and operations in AMD EPYC business unit. From Supermicro side, Junxia Zhou, technical product manager responsible for storage business from Supermicro. And from Xinnor side, we have myself and Sergey, VP of strategy. So why GPU performance is growing? It's not needed to be explained today. So everybody sees that on a GPU side, we see exponential growth of the performance year over year. Is it the same on a storage side? The best example is IO 500. IO 500 is the list of the most performant storage worldwide. And if you look in this list, you wouldn't see that storage performance is even doubling year over year. But what is performance bottleneck for AI workloads, especially for agentic AI workloads? It's storage for now, because the problem is how to deliver data fastest way to the GPU and not to make you GPU idle. To help me to be in more details related what's going on in the market, Sachin will help me, and I hand over to him from this.
Thank you, Dmitry. So basically, I'll just go over some market data points showing how AI is growing, and and how that translates to growth in storage that we are all seeing over here. So I think the first slide is not showing up. Yeah, okay, it takes some time, I think. So essentially, as we all know, ever since ChatGPT was unveiled in November 2022, December 2022, the generative AI industry has been growing at a very rapid pace. Initially, it was in the training from model parameters increasing from hundreds of billions to like the GPT-5 being 2 trillion plus, and Grok 5 being even more than that. And all that has resulted in models getting smarter and resulting in more inference uses across industries like healthcare, like energy, utility, or even if you look at it from various other industries like vibe coding and technology and so on. So across a wide variety of industries and wide number of use cases. And that has resulted in significant growth in the AI industry. And if you go to the next slide, it also shows you some data points for this one, the statement I just made. It's resulted in growth in like accelerator TAM. So this is a slide which shows accelerator TAM, and as you see over here, it's growing at around 60% CAGR overall, with inference of that growing at 80% CAGR. And in fact, this slide has been revised up with upward numbers for I think 1 or 2 times now, and I think sure it's going to be revised up even more. But even then, it shows that it's a very fast and steep growth that we're seeing over here from $45 billion to $500 billion as we see for training and inference as such, with inference occupying the majority of it as we go into the later years, as is expected. And there's another data point, which is the next slide, which is from the CPU point of view. Again, this is showing strong growth in CPU TAM, as we see over here, and growing at 20% CAGR. Again, these numbers will be revised upwards because one of the key drivers of CPU is essentially specifically for AI. Not the only one, but one of them is being agentic AI. And we did hear from several industry leaders in earnings call it just was happening last week or two, that number of GPUs to CPUs for training, if it's 8 to 1 for training, it would be 4 to 1 for inferencing, and then for agentic AI, it could go all the way to 1 to 1, and even flip the other side in favor of CPUs. So there's a significant demand for CPUs, which is translating even for as part of this agentic AI workload, as well as part of the broader generative AI segment. So if you look at all this AI translates to significant growth in storage. So the next slide essentially is showing you this growth in storage and how it's growing at. And that's very important because Xinnor is playing in the role of storage, as Dmitry just mentioned about. And it's done so that we can feed the GPUs to keep GPU utilization significantly high. So this is basically the impact of storage from generative AI industry segment and others also. This is specifically for the data center. And as we see over here, it's basically growing at 2 zettabytes to around 7 zettabytes, around close to 30% CAGR, with SSD and HDD also growing at pretty much similar rates. The key thing is that SSDs has largely not been used. Around 10% of the data center is historically for SSDs and 90% is HDDs. But SSD share for AI is increasing, as we see on the right-hand chart. Over here, it shows for 2025 is around 7% of entire industry growing to around 20% specifically for AI SSD shipment forecast. And this is important because for Xinnor, as we see over here, we want to feed the GPUs, and essentially this leads to having SSDs being the one which would be more prominent. HDDs can work, but SSDs are more prominent because you have high IOPS. Like for SLCA-based SSDs, you can have around 1 million IOPS. You can have hundreds of thousands plus of gigabytes a second, even for something like QLC SSD. Whereas for HDDs, it's in 100 to 200 IOPS and around 200 megabytes a second. So with SSD, Xinnor works extremely well, and of course with HDDs also. But as I said, it's more for SSDs that we would want, so that the GPUs are not starved. So if you go to the next slide over here, I will just show just at a very high level the path of storage. Some technical details over here. Path of storage from SSD to CPU DRAM, and then from CPU DRAM to it goes to GPU via traditional TCP/IP route and versus NFS or RDMA. So the left-hand side is the traditional TCP/IP route, and essentially over here it's very slow because the data moves from PCIe to kernel buffers, and then CPU essentially does a read and write from kernel buffer all the way to system memory. So CPU utilization is lower for other applications, which is what its main role is supposed to be. And also it results in a much higher latency and more costs. And more importantly, it takes time to feed the GPUs, because the path to GPUs would be essentially going via the CPU to the system DRAM, and then back again via PCIe to the GPU, as it's mentioned over here. So these are some of the challenges with the traditional route. And essentially, if you look at NFS or RDMA, it basically it's a zero copy method. It goes from the SSDs via NICs and essentially does a zero copy all the way from that to the system memory, bypassing the CPU altogether. And in this case, and it just informs the CPU once the task is done, the copy is done. And the route back again is pretty much the same thing. It goes via the CPU to the GPU. But more importantly, as I mentioned over here, there are a lot of benefits in the sense that you don't need the utilization is significantly higher because the CPU is not being bypassed, and it's only informed when the copy to the DRAM is done, and that leads to higher utilization for other applications. It also results in lower latency to the GPU. It also results in lower cost, and more importantly, as I put some data points over here, the number of cores which is used is reduced significantly, around 90% by NFS or RDMA, which again translates to lower costs and better utilization overall. So if we go to the next slide, I just wanted to also mention about AIS, AMD Infinity Storage. Now, the left-hand side was the same slide that I talked about, NFS or RDMA. And with the right-hand slide, we have AMD Infinity Storage. This basically takes directly from the SSD all the way to PCIe to the GPU HBM. Now, this is faster, but it's much more complex because you need to have some configuration. The kernel drivers must match the OS drivers of all the nodes, and PCIe topology must be optimally configured. It's much faster than NFS or RDMA, but more configuration is needed, and also you don't need it all the time. That's the most important thing. NFS or RDMA is very simple, straightforward, and with xiNOR's technology, you can achieve significantly high bandwidth. So if it's compute bound, as we see in the next slide, we will see that essentially you won't need it so much to that extent, because let's say a simulation run takes like 10 seconds, and with GDS you can get it in 1 second. What would the data do? It would just be waiting for the first part of the data, which is part of the simulation, to be executed. So NFS or RDMA may be slightly slower, but it's in such cases you really don't need it. And in situations wherein where Agentic AI, pre-processing, post-processing, and we'll come to that later on. That's an example where essentially CPU needs to be touched first. So as I mentioned over on the left-hand side, the general rule of thumb, which processor is based on which processor needs to touch the data first. So if it's CPU, for example, for pre-processing, post-processing, some feature engineering activities, and then handing it over to GPU, then definitely xiNOR solution with NFS or RDMA works best. If it's something which can be directly loaded, like video analytics, for example, then yes, I agree. Then it's basically AIS would be the one which would go for. But as I mentioned earlier, agentic AI is one of the areas where you need NFS or RDMA. So this would be something which would be a fast-growing industry, and there's some slides I'll show you later on. So that's basically the summary in terms of the industry that xiNOR's solution is operating in, which is basically the fast-paced, high-growth SSDs, and also how it feeds the GPU, and also the fact that not every time you need GDS, or AIS, AMD Infinity Storage equivalent. You can do very well with the NFS or RDMA, which is easier to configure and faster to set up and achieve speeds which aligns with what the GPU needs. So that's basically my slides on this. I'll turn it over to Dmitry on this.
Yes, thank you, Sachin. Thanks so much for deep technical overview of the current market status, as well as overview of the technology. So I encourage everybody as well to ask all the questions in the chat. We will be more than happy to address all of them at the end of our webinar. Going further, Sachin told us that technology will require much more performance tomorrow than it required today, and how the data could be fed to the GPU. We as well should take into consideration that AI teams, they are not teams which are from the scratch. Typically in enterprises, it's their teams who are specialized in particular research area, particularly important for enterprises. The same story about startups, the same story about neoclouds for everybody. So when we are discussing about data delivery, the most traditional way to deliver data for today, it's about file workloads. It's about file workflows. This way, data could be provided via shared access. As well, it would be compatible with all the existing tools, scripting, and environment existing on the customer side. And the last but not least, that it's ideal for Linux native teams and POSIX-based workflows, because most of the teams in AI today, they do POSIX for their day-to-day operations. So file workflow matters. The question is how we can provide the best possible performance and the best possible solutions for the file workflow. For sure, for large-scale installations, the most usable way to provide performance is a parallel file system. It's old but well used Lustre, BGFS, IBM scale deployments. Basically, high performance parallel file system. It's a solution for large-scale infrastructure. When you have several hundreds or even several dozens of storage nodes, then you need a parallel file system. In case if you don't have such scalable storage infrastructure and still you have a lot of GPUs in your infrastructure, what storage solution you could deploy? Many teams try to do it with do-it-yourself network-attached storage solutions. But do-it-yourself network-attached storage solutions seems to be too complicated, because you can reach great performance with this solution, but tuning all the stack for such solution is very difficult, time-consuming, and as well for end customer, it's absolutely unclear who will be responsible for the complete solution, as it's a typical use case for every do-it-yourself solution. Therefore, we made a decision to team up with AMD, Supermicro, and Xinnor and provide something new to the market. Basically, we formulate our task in the following way. First of all, we should require simplicity out of any deployments of our solution. Our solution should be deployed not in months, not in weeks. It should be deployed in hours and days. It's requirement number one. Requirement number two, it's all about performance. Out of your NFS storage, in practice, you can get more than several hundreds gigabytes per second throughput. The question is how to make this performance sustainable and how to tune all the NFS stack that end customer wouldn't need to do such tuning by themselves, and all the responsibility for saturating of the network would be on storage solution itself. So it was exactly the task that we formulated besides us, team up with Supermicro and AMD, and created a solution which we call xiNAS. So foundation of the xiNAS is a very fast data protection engine which is developed by Xinnor. We call this RAID engine xiRAID Classic. So it has two unique characteristics. First of all, it's a CPU-assisted way of parity calculation. How we do it? We use AVX instruction. We do our patented mathematical algorithms. We do our own way of data placement in CPU registers. Therefore, we can provide parity calculations much more faster than all the other guys. And the beauty of this solution is that it's software only. For storage, you don't need to have any hardware accelerators. You don't need to have any GPUs waiting just for parity calculation for storage. It's software and it's consumed very low CPU cores. The second cornerstone of RAID engine is a lockless data path. What does it mean? It's very simple. So all the workload is evenly distributed between all CPU cores. Therefore, you don't have any spike of loads and you don't have any bottlenecks in all modes of using the storage, including degraded and rebuild mode. So on top of our xiRAID Classic, we implement NFS. But let's see on the numbers that we can get together with Supermicro and AMD in our joint validation test. This test was as well done with Kioxia in their lab, and we used AMD EPYC CPU and Supermicro server with 24 drives. All the drives were Gen5 Kioxia drives. So we can see out of the graphs that from the single server node, we can get maximum possible performance, which is more than 300 gigabytes per second on sequential read and 100 gigabytes per second on sequential write. As well, we can have great numbers in random, which is more than 60 million IOPS in random read and 8 million IOPS in random write. So the question is, how we can expose such great performance out of the server to the real customer application? And here xiNAS shines. So let me explain very simple what it is. So typical xiNAS installation, it's several server nodes. Typically, we propose to use from 1 to 4 server nodes because you don't need to use more than 4 server nodes to saturate the network. Taking into account all the numbers I demonstrate in the previous slide. What we do? We tune NFS server stack, but evenly important, we tune NFS client stack that deployment of the solution would be very easy to the end customer. And how easy it is, let me hand over from this to Junxia. She will help me to explain more details why Supermicro servers matters in this deployment.
Thank you, Dmitry. Yeah, so I would like to start with how Supermicro servers fit best for Xinnor solutions. First is the high performance compute, the GPU plus the NVMe density that provide the data intensive workloads. As the Supermicro provides the industry leading GPU servers that it can effectively handle the data intensive workloads. So it ensures that Xinnor can support the demanding AI and HPC environment. The second one is the flexible and composable hardware. As you know, Xinnor is a software-defined storage solutions, so it benefits from the flexible mix and match components. And the Supermicro excels here. It can offer a wide range of storage platforms from for example, the chassis. We can support the 1U to 4U chassis. And for the storage service, we have all kinds of selections, like we can support the TCL and QCL drives, and we also support the E3.S, U.2. So you have lots of options to build the Xinnor solution on those high performance drives. And we also have the air-cooled and liquid-cooled designs that to help improve the operation efficiency. And the third one is the optimized networking gears. Xinnor relies on the fast east-west traffic for the distributed storage. So Supermicro supports the high-speed networking infrastructure, helping reduce the latency, accelerate the data movement, and improve the rebuild times. And lastly is the cost efficiency and the supply resilience. As you know, in today's environment, the supply is constrained and the hardware cost is rising, especially for the NVMe drives. So Supermicro and Xinnor together can provide cost-effective solutions. So it helps optimize dollar per gigabyte and dollar per throughput. So next one, I would like to introduce the reference architecture we have done with Xinnor, and we build the solutions on AMD EPYC CPU. First is the data nodes. We also call it a NAS server. It is the core of the setup. We built it on Supermicro AS-1116CS-TN platform. First, we have the high core account. We use AMD EPYC 945548 cores, and we have 384 gigabyte DDR5 DIMMs. So this is very critical for handling parallel workloads. And the second is that we have 12 PCIe Gen5 SSD OSHA drives, so we don't have any hit any bandwidth limitations. And on the client nodes, we also call it the load generator. So on this client side, we intentionally put the over provision the 64 CPU cores, AMD EPYC 9535. So we did this intentionally, just want to make sure that the clients are never the bottleneck. And all those servers are connected with NVIDIA SN5600 high-speed networking switches. And on each service, we put Mellanox CX7 400 gig NIC cards. So both both the high-speed switch and the NIC cards can provide the low latency and higher throughput compared to the traditional TCP/IP protocol. And we have already validated the Xinnor solutions on Supermicro AMD servers. But if you have preferred servers, we can also do the validation for you. We can make sure that we can deliver the total solution to the customer in a reliable status. And the next one is I would like to walk you through how we deliver the Supermicro Xinnor complete solutions. So first, we will start with pre-validation to ensure that the Supermicro Xinnor solutions is reliable and ready to deployment. So this includes joint testing reference architecture, and we verify the performance through the benchmarking, so the customer know how exactly what to expect. And we have, so at the end of this stage, we have a fully validated end-to-end solution. The next is that the quotation and order process. So we usually begin by understanding the customer's requirements. That includes the customer's workloads, use cases, their current existing networking environment, their capacity, and their data protection requirements. So based on that, we will select the pre-validated solutions or any customer's preferred servers. Then we will generate a bond to the customer, and we will move toward, if we get a confirmation from the customer, we will move toward the order conversation. So once the order is confirmed, we move to the production and delivery. Usually we will build the servers in Supermicro factory, and then we will have our engineer to install the vast the xenogolden images on the hardware on the servers. Then we will connect the hardware keys. So we will use the hardware keys to generate the license key. So once we ship out these hardwares, we will also send the license key to the customer. So the customer only just input the license key, and they can activate the Xinnor services by themselves. So overall, this process ensures a smooth, validated, and sufficient delivery. So minimize the risk and enabling customers still go into production quickly. So I will hand it back to Sachin.
Yes, thank you, Junxia. Thank you, Junxia, for your straightforward explanation how easy it is to get predefined xiNAS to the end customer deployments. So let me as well ask Sachin to help us to explain why AMD EPYC processors makes real difference for xiNAS solution on a technology perspective.
Yes, thank you, Dmitry. So if we go to the next slide, that shows, So I'm just giving a quick overview of the EPYC CPU journey, since we have a very broad audience. So EPYC CPUs are used in a variety of workloads. As we say, it's in HPC workloads, AI-related workloads. It's also used in general purpose workloads like database, analytics, social media, and so on. And it's being used by in several cloud instances by major hyperscalers, as well as multiple OEM platforms, as mentioned over here. The key thing over here is, if you look at the chart on the top, it shows the market share. And the key insight over here is, one is the rate at which it's been growing. It's been phenomenal growth, starting from 2018 of 2% and growing steadily all the way to 40%, which is current market share. And this is by a third-party research, as mentioned over here in the footnotes, Mercury research as such. So the key thing is that EPYC has been evolving at a very rapid rate in terms of their innovative technologies, in terms of the features that is being provided, and that's the reason for the high market share, which is basically says that there's a large variety of customer adoption across a variety of workloads, which is leading to this large market share. So that's basically a quick overview of EPYC CPU. Now we'll get to the next slide, which shows the architectural features, which essentially helps Xinnor's solution as such. So if you look at it from a Xinnor solution point of view, what it essentially does is it's used to pool the drives and bring the data exported by NFS, bring it over to the CPU RAM, and from there it goes all the way back to the GPU. So that's one is the forward path to the CPU RAM, and then once the activities are done, you need to essentially put from CPU RAM all the way back to and log it to the storage. So that's another part of it. And as part of that, there could be drive failures. So Xinnor solution also helps in this. So I'll take you through each of those. So in terms of pooling the drives, the first part wherein you're actually getting data and reading it to via NFS or RDMA solution from Xinnor. The higher the number of PCIe Gen5 lanes is very important, because now if you have a high number of PCIe Gen5 lanes, like it is there for EPYC architecture, it's 128 lanes for 1P and 160 lanes, up to 160 lanes in 2P, and that too with high-speed PCIe Gen5. All that means is that PCIe Gen5 speed is not the bottleneck. So per lane you can have 32 gigabits per second, or divided by 8 is 4 gigabytes a second. That is per lane, by the way. So you can have around 3 or 4 lanes, which is helps to saturate even the fastest SLC SSDs. So that's like around 14 gigabytes a second. So you can pull key point here is that you can pull a large number of drives at the same time, as you can also have connections with the NIC, with the GPUs, and all with one CPU as such, because the high number of lanes. And essentially that helps a lot, because now when you're with Xinnor, as you're pooling the large number of drives, you also need to do protection of the data. So things like erasure coding, cyclic redundancy check, parity calculation, checksum, and so on. And those are extremely heavy-duty calculations. And with AMD, we have AVX 512. This is the Turin CPU with AVX 512. And essentially, you can also do a lot of, do activities on large chunks of data, which would normally take multiple cycles of CPU. You can do it in single cycle, almost to a single cycle. So which means that you're essentially helping to, and that's done with the help of xiNAS solution. So which utilizes the architectural features of AMD, as I mentioned over here, AVX Python. So that basically helps to speed up the performance significantly, and basically presents the data, at a very fast pace, hundreds of gigabytes per second, which would not be possible otherwise, because the cores would be using their activities by processing in single sequential cycle, versus what is being done with AVX 512 is essentially almost parallel. As such, you can work on multiple chunks, large chunks of data in a single cycle. Then if you look at it from the RAM as such, so as I mentioned earlier in one of my charts, was that it goes directly with zero copy, and it does not put a lot of burden on the CPU cores, because it's bypassing the CPU cores and goes to the CPU DRAM, which is basically what NFS RDMA solution from Xinnor does. And in doing so, essentially having a large RAM helps. We don't need up to 6 terabytes, but I'm just mentioning over here that we can have up to 6 terabytes, 12 channel DDR5, and at a very high bandwidth as such. So 6400 megatransfers per second, and roughly around 600 gigabytes a second. We don't need such high configuration, but if it is there, it's much better from an architectural point of view, because the latency times to read from memory is, like, for example, I would say around 100 to 200 nanoseconds from a DRAM, versus reading from an SSD is roughly around 1 to 10 microseconds, depending on the type of SSD. And HDD is even larger. So this is the architectural feature from AMD helps significantly, because now you can avoid repeated trips as such, because of the large memory pool. Although we don't need such a large memory configuration, as I mentioned earlier, as was shown by Junxia's, the configuration which was used in the test as such. Then if you look at it from a core point of view, cores are important because they're performing the operations, as I mentioned over here. With AMD, essentially you have highest core performance and highest socket performance. So highest core socket is basically a combination of multiple cores, and you can have up to 192 cores. You don't need so much. You can have essentially deal with around 48, 64 cores, as Junxia mentioned also in the test that was done. But the key thing is that it is available if you choose to. And with having such a large number of cores, the benefit is that you can use the lockless approach from Xinnor solution. And the benefit is that if you go with a locked approach, then the scheduler needs to know which cores are locked, were being used, when it is finished, then unlock them. So all this layer takes a lot of time. With the lockless approach, you can have data stripes being assigned to the cores, and having large number of cores helps significantly. If you did not have a large number of cores, then obviously you cannot use the lockless approach to that extent. You can still use it, but not to that extent as CPU, which has a large number of cores, as mentioned over here. So in this case, this helps to speed up performance because of utilizing Xynor's lockless approach and AMD's large number of cores. And then finally, if you look at it from a per core performance, this is essentially a 3 nanometer node. You can also have a 4 nanometer node configuration. It basically means that you can do a lot more compute with the same power as a higher nanometer node. In addition to that 3 nanometer configuration, there are other technical features which helps to improve the performance. So for example, you can have better branch prediction, better execution engine, out of order execution, speculative decoding, and all such things. So all that leads to a higher instructions per cycle, and essentially translates to higher performance per watt, which is what is needed. So all in all, as we see over here, we have from a compute point of view, which is needed as part of Xinnor solution, you need higher performance of the cores and number of cores, as well as from PCIe Gen5 lanes, you also need large number of lanes that is provided by EPYC CPUs. And then finally, one more last thing which I forgot, essentially, is that as part of any activities, any installation, there can be drive failures, and the key thing is to how fast can you rebuild those drives. And with Xinnor solution, as I mentioned over here, you can do it much quicker. Basically, because as part of rebuilds, you need to work through several XOR operations, and then using AVX 512 for this essentially speeds up the performance significantly. So having lockless approach, having AVX 512, large number of cores, all that helps to speed up rebuilds. So in the case of a typical CPU or a non-Xinnor based NFS or RDMA, what would take days, you can do with EPYC CPUs and Xinnor solution, you can do it in hours to the rebuild, to do a rebuild. So that helps performance significantly. And while the rebuild is being done, there is no core contention. So the applications can still use the other cores, as I mentioned, because of the lockless approach and assigning data stripes to the cores. So all this leads to the applications not being throttled when the rebuild is being done. So you can achieve up to 90% of performance in that situations. So that's basically from an architectural point of view. So I will go to the next slide, wherein I'll show you an example with an agentic AI. I chose this, like Xinnor solution can be used across multiple workloads. I'm just showing agentic execution because in the current time frame, agentic AI is being referenced a lot, and for a valid reason. And this huge growth for agentic AI. I have a slide next one, but let me go through this. This is just a very high level overview, and it shows you how Xinnor solution plays a big role in the agentic AI. And this gives an example of like finding the largest opportunities to win. So in this case, the first stage, of course, before it's passed to GPU, you need to essentially parse this, detokenize it, and maybe you can use a JSON object to understand what the query is, even in a CPU. Um, and do some executions. But if you cannot, it's translated to it's basically moves to the GPU, and then that by lang chains kind of technology. And once it's there in the GPU, essentially it is able to use pre-filled decode, understand what it is, and GPU sends back the context and what is the activity needs to be done. It goes all the way back against the CPU. And from the CPU, again, there may be activities like, for example, reading a Salesforce database like CRM database, or it could be vector database, or you may need to do retrieval augmented generation. So a lot of activities which need to touch upon storage. And as mentioned over here, whenever we have the storage, definitely having Xinnor solution helps significantly. And in this case, I've shown over here Xinnor solution, which is takes data back and forth from the SSDs all the way, that's the personal data, and all the way to the CPU for pre-processing, sends it to GPUs. And then there's also post-processing activities. So once you have all the data, and the GPU has done the gone through it, understood the context, and done the necessary task, it passes it back to the CPU, probably maybe just to create a summary or sort it. That can be done. That's a CPU activity which can be done. You really don't need a GPU for that. And then once that is done, you may have to you send it to the user, but you also log it. And again, over here, SSDs need to be touched. And as part of that, Xinnor solution plays a big role in this. So overall, as I mentioned over here, in the fast-growing agentic AI space, EPYC CPUs powered by, of course, which are also in Supermicro servers and powered by Xinnor solution, add significant value in examples like this, which I mentioned. And I'll go to the next slide, wherein I just show how the agentic market is evolving. Just a few statistics over here. We heard about Agentforce from Salesforce, essentially then how fast it has grown. It essentially had 300% increase, reaching ARR of 500 million in, I think, 6 months to around 10 months from the inception. HubSpot has several agentic AI solutions like Breeze Agent, Prospecting Agent, and used by a large number of customers, as mentioned over there. And then SAP has a Joule agent, around 40 specialized agent, and several other companies also like ServiceNow, Monday.com, Workday. So agentic AI is being used by a large, broad number of ISVs as such. And that translates, it's also translating the big TAM, as we see over here. Now, this is essentially, you should take it more for directional rather than absolute numbers. But the key message over here is it's growing at a very fast pace, like 50% CAGR, as we see by the two sources which have cited this, the TAM as such. And the key point over here is that it's still in its early stages. It has a fast and a high growth in the coming years. And having Xinnor solution and play with EPYC CPUs and powered by Supermicro servers has a significant impact, positive impact to the end customers. So that's basically what I would like to end with on this. And I'll turn it back to Dmitry.
Yes, thanks so much, Sachin, for very deep analysis and technical insights. I encourage everybody to ask questions. I see the question from Paul. I hope that there would be other questions as well. So as a conclusion, so how to run xiNAS installation? It's very straightforward and very simple. You should just get xiNAS server from Supermicro or your Supermicro partner, power on the server. After that, you should install xiNAS client on every client PC. Open xiNAS client menu and mount NFS share. After that, you should enter IP address of the server and mount is created with high performance defaults. So it's done deal, and for end customer, it will take just several dozens of minutes to have this solution fully operated. The last but not least, what is important, xiNAS has as well a model that we call HealthCheck. This model helps in day-to-day operation of the solution and fix all the problems that solutions see in day-to-day operations. As a add-on to our webinar, we will provide to all the participants a short video how xiNAS who could be reached out through MCP agents. So Agentic AI is not only the target use case for us, but as well it's on place in development and using our solution. So this video would be available with the record of the webinar tomorrow. So going to the numbers. Going to the numbers. If you can see just from single node xiNAS configuration, which is server with 12 NVMe drives, with AMD EPYC CPU and 2 network cards. This case, it was BlueField 3, but it's not mandatory to use BlueField. You can use whatever network connectivity you would like to have. It could be as well connectivity for sure. And what we built for data protection, we use RAID 6 over 12 drives, and in all the drives we as well split a small namespace for RAID journaling, for file system journaling, that will improve overall performance of the installation. So what you can get as a result, just from a single node configuration, you can get more than 70 gigabytes per second in read and about 40 gigabytes per second in write. And it just from a single server. How this configuration could be scaled out? So if you use 2 xiNAS server nodes, then this case you can get more than 100 gigabytes per second in sequential read and 80 gigabytes per second in sequential write. Basically, it's network saturation. So you don't need to have more xiNAS server nodes in case if you have 400 gig networks. It's a reason why for such type of deployment, it's not needed to use as well all the complexity of the parallel file system, and you can get all possible performance out of relatively simple installations. What is well very important, it's degraded and rebuild mode. Sachin previously told us why it could be very effective in our joint solution. So let's look on the numbers. And we can see that we have in a degraded mode just 10% penalty for read, and we have almost no penalty for write at all. It's thanks to overall architecture of the solution using AMD EPYC CPU, Supermicro servers, and Xinnor xiRAID software, as well as tuned NFS stack by all of us. So in degraded mode, just 10% of the penalty. So instead of the conclusion, what we are proposing? We are proposing very simple and easily deployed solution where you don't need to configure your own data protection. Everything related to the RAID data protection as well pre-installed in and in place. In case if you would like to change something, you are welcome. You can do it through user interface, or we can provide you with the MCP agents help you to solve this task. As well, you don't need to do any NFS tuning. You need to Google to any client mount options and to take all the headache how you can should mount multiple clients and get maximum performance out of the clients. Everything you can get out of the box. And as well, we hide from you all the complexity of the RDMA as transport protocol itself. So basically, that's it. And I think it's now right time to go to the questions. I see 2 questions in the chat, and it's now still time when you can ask additional questions. So we have a question from Paul. For a smaller AI HPC team, for a smaller AI HPC team, what would be a sensible AMD EPYC starting point with xiNAS? Sachin, I think it's a question to you.
Sorry, I can't see the chat here. Oh, what would be a sensible AMD EPYC starting point with xiNAS? Okay. So the configurations are essentially, the number of cores that you need. So you can have around 48 cores, 64 cores. You can also have, you need RAM for it. So around 400 to 600 gigabyte RAM. So that would be helpful. Number of PCIe Gen5. So we have around up to 128 lanes as in for Turin. Now, in the case of what would be the right sensible configuration to use, it depends on how many drives that you want to pool. So in the test which was conducted with Xinnor using AMD EPYC and Supermicro solution, I think there were 12 PCIe Gen5, 12 drives actually. 12 drives were used and lanes were used for each of this. And essentially, if you're using within the drives, if you're using SLC, then you need to have enough number of lanes per drive to saturate the SLC speed. So SLC speeds are roughly around 14 gigabytes a second, but if you're using QLC, it's much lesser, probably around 10 gigabytes a second or even lesser than that. In this case, you need lesser number of PCIe Gen5 lanes. So each lane you need to know is essentially you can have 32 gigabits per second, which is 4 gigabytes a second. So if you have QLC with 8 gigabytes, which is the drive speed for read, then you essentially need 2 lanes for that. If it is SLC, then you need around 4 times. This you can't be having 3.5 lanes, so you need 4 lanes for that per drive, and depends on the number of drives that you need. And the number of cores, essentially, again, that's based on what is the end application that you're looking for. But if you're assigning data stripes to cores, so that it's a lockless approach, and you're using data protection, which you need, then you need AVX 512. You need around 48, 64 cores, as I mentioned. That should be good enough for it. So that's at a very high level, I would say, the EPYC configuration that you would need.
Okay, thanks, Sachin. The next question, please discuss the recovery time for different RAID schemes. Thanks for the question. It's exactly where our solution shine. I demonstrated in a slide that with RAID 6, we have just 10% penalty in degraded read and almost no penalty in degraded write. So we have as well a customer who already use this solution in RAID 7.3. 7.3 means that 3 drives are used for parity, and stripe width this case is 24 drives. And this case, the results are not significantly different. So it's as well about 10-15% of the penalty in a degraded mode. And it's thanks to the architecture of AMD CPU, as well as how we use instructions of the AMD CPU in our data protection engine. So the combination of two factors gives such small penalty for redundancy. And I would like to pay attention that it's impossible to get such penalty with any other GPU assisted solutions, because this case you would have all the traffic Sachin explained between GPU and CPU, and in this case the penalty would be much more higher. So you need data protection basically when something is wrong. And this case, if you pay for this just 10-15% from the normal mode performance, I think it's the best possible result that you can get out of the solution.
Dima, I think the question is about recovery speed. So there is no difference between recovery speed for RAID 6, RAID 5, and RAID 7.3, and recovery speed is only limited with drive performance because we need to read the data and write data back.
Yeah, absolutely. Thanks, Sergey, because related to the drive rebuild performance, it is the same.
And one more point I want to mention over there is, as part of recovery, you need to do a lot of calculations which involve matrix operations, like checksums and things like that. And to do that, AMD's EPYC 12 helps significantly, because you can then process large chunks of data in a single cycle, or almost a single cycle, versus many number of cycles. And all this is being utilized by Xinnor's solution when they're running it in Supermicro, but also other OEMs. But for the test periods in Supermicro. And generally, if you compare with the standard solution versus the one recovery time with standard solution versus the ones being used by Xinnor's solution, I would say it would be essentially moving from days to hours. And at the same time, when the recovery is done, this is an important point, is that applications which are running on the CPUs should not be throttled. So because you have a large number of cores with AMD EPYC, and Xinnor is again able to use this large number of cores and use data stripes assigned to certain cores using lockless approach. All that means is that the other applications which are running while the rebuild is taking place, they can run at their own speed, and it's like roughly around, you can achieve around 90% plus of what they would be without the rebuild having taken place. So they're not being throttled as well. So that's another point I want to mention.
Yes, and Sachin. And the last question, how predictable is performance when going from one server to two? Sergey, please help me to answer on this question.
Yeah, okay. So it's again, mostly depends on your workload. By default, we say that it's close to linear scalability, but when we are dealing with NFS, the workload is split so file by file. One files go to one server nodes, other files go to the another server node. So for workloads, we have multiple storage servers, and you have one large file workload. We would prefer to utilize some solution with parallel file system like cluster or BitJFS or storage scale. But when you have multiple files, NFS-based solution is quite okay, and you will see linear scalability of performance by adding more servers.
Okay, thanks, Sergey. So I think that we are almost out of time because we are at the top of the hour. So thank you everybody for attending webinar with us, and thanks so much for all the speakers. Tomorrow we will provide a webinar recording with a special gift from Sergey related to the MCP agent, which would communicate with xiNAS server. And if you like to use this MCP agent, please feel free to reach out Sergey directly, and because he is a great fan of all the AI agentic development, not only for storage side, but as well in storage management side. So thank you everybody, and looking forward to see you again in our webinars.
Thank you. Bye.
Yeah.
Thank you.
Thank you. Bye.
Thank you very much.